All right, so we're doing area of a triangle, radians, arcs, and sectors. This is the last little bit of the trigonometry unit. And so you guys are gonna learn how to find the area of a triangle, different from what y'all know of 1/2 base times height. This is to find the area of any triangle now, as well as how to find lengths of arcs and areas of sectors. So a few formulas today, some examples to go along with them, and here we go. The formula for the area of a triangle, any type of triangle, is 1/2 BC sine A. Now do realize, of course, that formula of 1/2 BC sine angle A can change depending on the labeling of that triangle and depending on what what information you have. But essentially, if you know two adjacent sides and the angle that's included between them, you can find the area of the triangle. Okay, so in other words, a side angle side situation, you can use that formula. So here, as you can see, we have angle C, we have side A, and we have side B. So in this case, the formula would be 1/2 AB sine of angle C. Okay, but again, two adjacent sides and the angle that's included between. So then we just plug in 1/2 8.4 times 7.8 sine of 87.2. And so we'll type that in to find the measure of the area of our triangle. All righty? I'm using 0.5. Of course, I need my calculator to be in degree mode because the angle I'm working with is a degree. So then when I click enter, can we get this? Wonderful. So three significant figures would be 32.5. And then don't forget your units. It is squared because we're talking about area. So it's going to be centimeters squared. Okay. Of course, this is one of the more easier problems. You know, you have all your information. You don't have to find anything extra before you go and plug it into the formula. But it's very possible you might have to find the angle and then use the formula. It just kind of depends on the problem. But it's pretty straightforward from there. Or you might know, or you might be given the area like you are in this case. The area of this triangle is 50 centimeters squared. And you're asked to find the angle. In this case, the formula is going to be 1/2 what? Because I can't use BC sine A. I don't even have an A, B, and C. What are my two sides?
FE, lowercase f, lowercase e.
Lowercase f, lowercase e. There's going to be sine of angle.
Capital D.
Capital D. So my area is 50. So I plug in 50 for my area. I know that E is 13.7 and F is 8.2. Now it really doesn't matter. I could have done 8.2 and then 13.7. I'm multiplying it, so it doesn't matter which one goes first. Sine of angle D. How'd I solve this?
Don't you divide both sides by all the product before the sign?
I can divide both sides by that all those numbers before the sign. I'm going to go ahead and multiply those out. See if it actually gives me a number that's not too crazy. Yeah, it's not too crazy. So 50 equals 56.17. So then that way, when I divide, it's not nothing too big. So I have 50 divided by 56.17 equals the sine of D. Remember, whenever we're looking for an angle, we're going to do the what? The inverse. So D, angle D is going to be equal to the sine inverse of 50 over 56.17. You guys get this?
Yes, we do.
Yes,
Three significant figures would be 62.9. Good stuff. Questions on how you find the area of a triangle?
No.
Anytime you have to use a previous answer to maybe find the area of a triangle, make sure you use your non-rounded answers to do so. Now, beyond degrees, there's radians. Radian was actually like the first way that an angle was measured. Okay, so do be aware that there's two different types of ways to measure an angle. You have degrees, which you guys are used to from geometry and even a little bit in this class, but now you're going to be working with the radians. Angles can also be measured in radians. Radians are directly related to measurements within a circle. Okay, so you're more likely to see radians when they relate to a circle versus a triangle. But that does not mean that you can't have a radian measure as an angle in a triangle. If you do have a radian measure, you just want to make sure your mode is in radian. So what is a radian? A radian is actually, one radian is about 57 degrees, essentially. If you think about it, pi is what, roughly? 3.14. That 3.14 is the number of radians that's in pi. Pi is half of a circle. So there are 3 and roughly 14 radians that make up half of a circle. So that's 6.28. So about 6 radians and a little over a quarter that make up a whole circle. And a radian is defined as the size of the central angle subtended by an arc. So basically included by the arc, which is the same length as the radius of a circle. So essentially, this right here represents a fraction of the circle. All right. And again, its measurement is associated to roughly about 57 degrees. Why are radians important? Because anytime you're dealing with circles, such as what we're going to be doing when we talk about arcs and sectors, as well as when we get to the next unit that deals with the unit circle, you're going to be dealing with radians a lot. Okay. So the main thing you need to take away from this is that radians exist and we are going to be using them. How so? Well, in an arc length as well as area of a sector. First off, before you guys start to write, I just want to make sure everybody understands. Arc length is essentially the piece that goes along the circle, okay? A way to think about it is that it's a part of the circumference. Because remember, circumference goes around, it's like the perimeter of the circle. So arc length is a piece of that circumference. It's represented by the variable s. To find the length of your arc, you just take your radius and you multiply it by your central angle. Well, what's your central angle? It is the angle whose center is at, or sorry, whose vertex is at the center of the circle. So whatever that angle is, that central angle, you multiply it by your radius and you get your arc length. But the most important thing you need to be aware of is that the angle is measured in radians. If it's in degrees, you are going to need to convert it to a radian. We'll talk about that in a second. So S equals R times theta is how you find the length of your arc. Area is like when you get a pizza and you take a slice, that slice is a sector, okay? So it's essentially part of the area of the circle that you're taking away. That is found by doing 1/2 r squared times theta. Again, theta needs to be in radians. Beauty about both of these formulas, as well as the formula for the area of a triangle, all three of the formulas that we're doing today are in your reference booklet. So these two, along with your 1/2 BC sine A, they're all in your reference booklet. Now, I don't know specifically for the area of the triangle if it's 1/2 BC sine A or if it's 1/2 AB sine C, but it's in there. It is in there. Okay, so let's look at a few examples that deal with arc length and sector area. And then we're going to look at refreshing your memory on how to convert from radians, degrees to radians, just in case you're ever given a problem that gives you your angle in a circle as a degree versus a radian. So remember, to use either of those two formulas, you are going to need the angle as a radian. So let's find the length of the arc, which subtends a central angle of 2.6 radians in a circle of a radius 7. Subtends basically means that we want the arc that is created by extending our central angle so that it touches the circle. So we're basically looking for the length of that arc that I've colored in red. Well, very simply, length means we're using the formula S equals R times theta. Remember, theta has to be a radian, which we know is about 2.6 radians. My radius is 7. My angle is 2.6. And so then we just type it in and we get our arc. Go ahead and type it in. Tell me what we get.
18.2.
Confirmation. And because it's length, which is a part of the circumference, it's just centimeters, not centimeters squared. It's just the regular length. To find our area, the formula 1/2 r squared theta. We plug in again. I know my radius is 7, so I square it. And my angle, which is in radians already, I don't have to do any converting. I just plug in to get my area. Confirmation? And that's going to be centimeters squared. Make sure you don't forget about your units.
Oh, it's exactly 63.7.
It is. Now, of course, these are the more easier problems, right? So let's take it up just a little bit. Right? A circle has a radius of 2.5 millimeters. Find the size of the central angle subtended by an arc of length 9 meters. So even though there's no picture here, for those who need the visual, you essentially are looking for the size of the central angle. So you're looking for that angle there. You know it has a radius of 2.5 millimeters. And you know that the length of the arc is 9. So I'm still going to use S equals R theta. I'm just going to plug in my pieces a little differently. I know my arc length is 9. That's what S represents. I know my radius is 2.5. And so then I'm just looking for theta. Simply, how do I find theta? I divide both sides by 2.5. So theta is going to equal 3.6. And that is a radian. So 3.6 radians, which is roughly a little bit more than 180 degrees. So my picture is actually a tad bit off. I could fix it, which I am going to. Since I know that 3.14 is a full half of a circle, I'm actually looking for one that's a tad bit more than 180 degrees. Still good? Look at this one. In this circle, arc AB is 7.86 centimeters, and the area of the sector AOB is 23.58 centimeters squared. Find the central angle theta and the radius r. Here, I know both measurements, but I don't know any of the pieces that actually comprise to get those values. So that means that my arc, which is 7.86, we got that number by multiplying our radius and our angle together, which I don't know. And I also know that my sector, which was 23.58 centimeters squared, we got that by multiplying 1/2 r squared theta. So I have two different equations with two different variables that I need to solve for. How do I solve for those variables? You would use substitution. Remember, whenever you have two equations with two different variables, you can either use substitution or elimination to solve for those missing variables. Substitution will be the option we could do here, because elimination only works with linear functions, okay? And these are not linear. I'm multiplying two variables together. So substitution was we take one of the equations, we solve for one of the variables, we plug it in to find the other. So let's take the more simpler one. Which variable do you want to solve for?
R.
So that means I have to divide both sides by
Degree.
the angle. Okay. So R is equal to 7.86 divided by theta. So that means I'm going to plug this expression of 7.86 over theta in for R into my other equation. So that's 23.58 equals 1/2 7.86 over theta squared times theta. $7.86 squared is this decimal. I do not want to round that. I'm going to throw everything off if I do. So this is going to be 23.58. 1/2 times, that's gonna be my numerator, 61.7, help me out. It was over theta squared, because I gotta square the top and the bottom. And then I multiply by another theta. What happens to the thetas here? I can cancel one of them. So this theta goes away, and this is gonna turn into one theta at the bottom. I could actually apply this half here. I can multiply 1/2 to my numerator. So I'm going to divide this by 2 to figure out exactly what it's going to be. So now I have 23.58 equals 30.8898 over theta. How do I find theta? Multiply theta by both sides and then divide by 23. So I'm gonna multiply this side by theta, this side by theta, and then I'm gonna divide. So this turns into 30.8898 divided by 23.58. I'm gonna turn these into X's so they look like this. I'm gonna take this number divided by 23.58, and boom, theta is 1.31 radians.
Is it always going to be like 2 decimals?
This one happens to be the case because the arc length and the sector area were rounded. So, but it's very possible it could be a non-terminating decimal, but you still want to round to three significant figures.
Okay.
Then just to find theta, to find R, we plug theta back in. So that's 7.86 divided by 1.31. And what do you get? You get 6. That's nice. So our radius is 6 centimeters. So that was a little bit more involved. This is more like an IB type of problem. Okay. Only difference is IB probably will break it up. They probably have you find theta first, or find R first, and then find the other variable. Okay. So, like I said before, when you're finding the arc length of the sector area, you want to make sure that theta is in radians. So if you're ever given a circle that's in degrees, you have to convert it to radians. Anybody remember from algebra 2 how to convert from a degree to a radian? Pi is involved.
R plus R squared pi.
Y'all remember?
Wasn't it 180 divided by pi? Something like that?
Close. That's actually how you go from radians to degrees.
Ah, damn.
But if you ever have to convert from degrees to radians, you multiply the degree by pi over 180, or vice versa. I figured I'd give you both ways just in case. I don't know why you would need radians to degrees, but yeah, just to make it even. So it's very simple. You just multiply and you're good. This is going to be helpful when we get to the unit circle. Just in case if you ever forget what one of the radians are on the unit circle, you can always convert it and vice versa. The thing is too, even though a lot of the problems that we did with the sectors and the arc length had like 1.3 radians or 6.2 radians. These are correct. These are proper ways to represent a radian. But also realize that like 4 pi over 3 and pi over 2, these are also radian measurements as well. Okay? And to be honest, if you can, or if the angle is given to you this way, as like a number pi over another number, then leave it like that. Okay? Then leave it like that. So for these, when I'm going to ask you to convert each of these into a radian, have your answer be some number pi over some number. Some number pi over some number. Because if you want the decimal version, all you have to do is multiply the pi through. But leave it so that it's a number over pi. So for example, to convert 30 degrees to a radian, I multiply it by pi over 180. Well, that's just going to turn to 330 pi over 180. And I just have to simplify that. What number goes into 30 that also goes into 180? 30. 30 divided by 30 is?
1.
1. And what's 180 divided by 30? That's 60, but 6. So then 1 pi over 6 or just pi over 6 would be my radian. Okay? Over here, convert the following to degrees. I have 2 pi over 5. I want to multiply that by 180 over pi. That's how I convert it to a degree. What happens to your pi's? They cancel out because I got a pi on the top and a pi on the bottom. Now of course you can multiply straight across. I like to kind of simplify this a little bit more. Doesn't 5 go into 180?
Yes.
How many times?
40.
No, not 40.
30.
Not 30, so we're between.
35. 32, 31, 33, 34, 36, 37,
36.
I mentioned it.
Yeah, you mentioned all of them too. All right. And so then I would just multiply 2 by 36 to get 72 degrees. So 2 pi over 5 is 72 degrees. Okay. I want you to do B, C, E, and F, converting it to either degrees or radians. So when I multiply 43 by pi over 180, What did you get?
43 pi.
It didn't reduce?
No,
Can y'all confirm that?
see, I can't compare.
So you can't have a decimal.
You cannot have a decimal.
The calculator will reduce.
Except for, okay, so this one can't reduce. What about 60 degrees? Would that go down to?
1/3.
So then it'll be pi over 3. Now, 2.3 radians, even though it doesn't have a pi, doesn't mean you still can't convert it into a degree.
Mhm.
It's just this time your answer is going to actually have a decimal, because if you're given a radian as a decimal, your output is going to be a decimal for your degree.
Oh, no, it didn't have this.
Oh, it did? It was a whole number?
It was a whole number.
4/1/4 over pi.
Oh, okay, so then what's 414 divided by pi?
I have no idea. Don't even want to. Oh, wait, are we supposed to?
Yes, like, yeah, like give me a decimal for the degree. Antonio, what you get? So then it'd be 132, right?
Where's pi?
Pi is second caret. I mean, I'm not sure. I haven't done it in a while.
Oh,
This one right here. So 2.3 times 180. Then I'm going to divide that by pi. So yes, it would be 414 divided by pi, but we want the actual degree. And so it'll be 131.780, blah, blah, blah. So 3 significant figures would be 132 degrees.
that makes no sense.
Pi over 9, what did you get?
Oh, 90.
9 on 90.
Oh, wait, my bad.
20. There we go. Pi over 2 is actually 9. So again, you might need the skill of converting the degree to a radian if it happens to be that when you're talking about arc length or sector area, they give you the central angle as a degree. It always needs to be in radians. So you have your 3 formulas. All of them are in your reference booklet. Use them wisely.